Tell me. Hi everybody, so energy is the ability to cause change or do work. We were talking about this textbook, and I was wondering if I lift it up, does it have the ability to cause a change or to do a work from here?
Yes.
What would happen if I let go of the textbook? Oh, would that be like doing some work or causing a change? Yeah, right? So wait, does it have that ability right now?
Yes. No. Potentially.
Potentially it does. It's like hidden. It's not being released yet, but it's like stored in its position. It's there, right? That's called potential energy. This is the gravitational potential energy. I did some work to it. My muscles lost some of their energy, and they went into the book's position. Now, when I let go of it, what's going to happen to that potential energy? What's it going to turn into? Kinetic energy, which is the energy of motion. When it slams and hits on the ground, what's going to happen to that kinetic energy? Is it going to disappear and be gone forever? No. Or has it changed into some other forms of energy? Let's see if we can track what some of those changes might have been. Are you ready? 3, 2, 1.
It bounced.
Did it make a sound?
Yes.
Sound is a type of energy. It's a vibration of air molecules. That sound energy hit you right in the ear, and you felt it. Do you think there was some friction there? Yeah, those molecules on the floor and on that book are very slightly warmer now than they were before. All of the energy that was in its stored position got released as other forms of energy there. I do want to talk about one form. We're going to do a whole big unit on energy coming up later. It's going to be all throughout this year, really. But I want to just preview one form of energy. Is the energy of motion. That's called kinetic energy. Squeeze that into those notes somewhere. The kinetic energy is the energy of motion. Remember, it's the ability to cause change or do work. Kane, what position do you play in football?
Cornerback.
Cornerback? Mm-hmm. Do they ever send you on blitzes at the quarterback?
Yeah.
Okay, so let's imagine a situation where Kane is a cornerback, so he plays on the defense, and he's running towards the other team's quarterback. Kane, are you quick or real quick?
Quick.
He's quick. So he's got some speed, right? Kane's running, he's running in a straight line. Does he have some ability to cause a change or to do some work on that quarterback in that motion?
Yeah.
That's kinetic energy. There's that energy. We can actually calculate the amount of energy within Kane's body when he's doing that motion. We would take his mass, we would multiply it by the velocity that he's going squared. And then we'd multiply that all by 1/2. And that would be the energy that he has within him, and we can actually calculate that. And then sure enough, if you get a nice line-up shot on that quarterback, all of the energy that's in your motion, right into the quarterback. Right? Which is why football is a very dangerous sport, because maybe if you did it wrong, that energy could go into his brain. So be careful with your tackles. Tackle with appropriate form, please, Kane. Thank you. That's energy. Okay, what's your next note on your sheet?
What's temperature?
Okay, I'm building a story. Here's one fact. We've got energy. There's this energy and kinetic energy. Temperature is the measure of the average vibration of the particles in a substance. So when we measure the temperature of something, we're actually measuring the average vibration speed of all of the particles in that substance. If the vibration of the particles is faster, then that thing feels hotter to us. If the vibration of those particles are slower, then that thing feels colder to us. Had you ever wondered what temperature was before? We have this feeling, like, it's hotter. And you measure the temperature, like, what is that really measuring? It's measuring the particle speed. Okay, so I'm going to show real quick how a thermometer actually works. Like an old school thermometer. You know, they're like glass, right? It's like a long piece of glass. And then there's like a little bulb at the end.
Mercury.
And then, yeah, they used to put mercury in them. Do you know what they put in them now, because mercury is so toxic?
Alcohol.
Yeah, it's actually alcohol that they dye a nice red color. Wait. So we'll take that thermometer, and and we'll put it in like a beaker. Put it in a beaker of water. And the water has a certain temperature, right? If that water is warm, what does it mean about the particles in the water? Vibrating pretty quick. They're moving around, vibrating. Are they going to run into each other?
Yes.
Totally. Are they going to run into the particles of the thermometer?
Yes.
Yeah, they're going to bump into it. Those particles in the thermometer will very quickly speed up to the speed, the same average kinetic energy speed. Wait, if the particles in the alcohol are now vibrating faster, can they stay close together, or do they have to spread out a little bit?
Yeah, just spread out.
They spread out a little bit. You know how warm things expand, right?
So that's
Why do warm
fine,
things expand?
Because they're hitting each other and they're going farther.
The particles are vibrating faster, so they end up spreading out a little bit. Okay, if we've got the alcohol trapped down here in the ball, but it's trying to expand, where's the only place it can go? Right up the thermometer. So the thermometer rises because the particles are moving faster, so they spread out and they push themselves up. And we've like calibrated our thermometer so that we know that like this much rise, we're going to call that 1 degree Celsius, and that much we'll call it another degree. Let's go the opposite way. Let's put the thermometer in a cold beaker. The particles in the water are moving very slowly. Our thermometer was warmer than them, right? So the thermometer's particles will bump into the water, and they'll give some of their speed to the water molecules, and they will find an equilibrium. And the particles in the thermometer will be moving at the same speed as the particles in the water, pretty quickly. If the particles are moving slower, what happens to them? They can come a little bit closer together. So what happens to the red line? It shrinks, everything shrinks back a little bit, and so the red line comes down. A thermometer, it's really a speedometer. It's measuring the average kinetic speed of the particles. That's kind of cool. Okay, really quick check. Here's a section of gas. Here's that same gas in a different situation. The arrows show the speed of the particles. Shout it out. Which one's hotter?
Right.
Right side's hotter. Look, the particles are moving way faster. This would be hotter gas. This would be colder gas. Okay, I think you guys are getting it. This next slide is not for everybody. It's for the students who are ready for this. If you see this slide and you just go, what? Just try to hold on for the ride. I'm not going to test you on it, though. In a substance, the molecules are not all moving at the same speed. Some of them are moving faster, some of them are moving slower at any moment. It's constantly changing because they're bumping into each other, right? And so maybe like 2 or 3 molecules will bump into one molecule and suddenly give it a lot of energy. And then other times, like a molecule might have given its energy away, so it'll have very little energy for a moment. And moment to moment, there's going to be a distribution spread of how the molecules are behaving. And this graph shows that typical distribution spread. We'll see, this is the number of molecules. So if you go up this, you're saying there's more molecules there. And then this is the average kinetic energy of those molecules. So we see that in a substance, there's always going to be a few molecules, see not very many molecules, a few molecules that have very low kinetic energy at any moment. Then there's going to be more molecules, so I'm higher on this graph, that have like whatever the average kinetic energy is. There's going to be most of the molecules there. But then you'll notice that as you go in increasing kinetic energy, there will be a smaller and smaller number, but a few molecules with that kinetic energy. So that particular particle in the substance might be very, very hot for a moment. Interesting. It's called a Maxwell's velocity distribution curve. It's sort of a bell curve. You'll notice it's not a perfect bell curve. A perfect bell curve would be even on both sides. This bell curve skews and has this like long trailing tail of like a few very fast particles in any substance. There will be a few particles for a moment that are very hot themselves. When we touch it, we don't feel those individual hot particles because they're so small. We feel the average kinetic speed of all of them averaged together. Have you ever wondered why like a cup of water just left out in the room will just evaporate slowly? Here's what's happening. There are a few particles that are way on this high energy side that have enough energy to escape as gas. Okay? But in the water, they also have to be, if they're down in the water, they'll get that energy and they'll be like, I want to get free, and they'll just run into the next water molecule, right? And then they're still in the sample. But if that molecule happened to find itself getting bumped into by like 3 or 4 molecules, and it was on the surface, guess where it goes? So there'll always be a few molecules in the sample that for a moment will have that energy, enough energy to escape as gas. but they need to be right on the surface to actually make it. That's how, oh, here's the interesting thing. They're pretty hot when they escape. They take with them all of that kinetic energy. They take that energy from the sample. They take a lot of energy with them. That's why when you sweat, it cools you down. Because that water gets pushed out onto the surface of your skin. As it evaporates, the molecule takes that energy with it. And you are cooled down a little bit. That's super cool, right? That's real cool. Okay. Interestingly, this is like advanced stuff right now. This is the distribution curve of those molecules. Here's a cold sample. You'll notice the the distribution is much tighter. They're colder on average, but they're also closer together in terms of the spread of molecules, because to be cold is a little bit more of an ordered state. As we heat that same sample up, we don't take the curve and just move the curve warmer. What we end up doing is taking the average and moving it warmer, but to be hot is a disordered state. There's more movement happening, and so you'll end up with this wider spread. You'll have more molecules that are hotter, but you'll also have molecules that are colder. And so the average moved, but it also sort of like spread out. You'll notice here, if this was cold water and this was warm water, let's imagine that this is the line where if you're on this side, you have enough energy to evaporate. Which sample has more molecules that could evaporate at any moment? The warmer sample, so that's warm water is going to evaporate faster. That's why.